Hi, this is Joshua Gaus. I'm presenting my final project video for remote sensing under Dr. Steve Mitchell. The goal of this project was to build and use a computer vision-based LiDAR scanner in order to better gain an understanding of the basics of remote sensing and its use in the field. As part of this process, we selected and scanned a target from around campus. This process was moderated by Dr. Mitchell, whose long-term goal is to build up a LiDAR point cloud map of the entire campus. In order to spread out scanning across campus as much as possible, each student would submit their top 3 choices of target to Dr. Mitchell, who would then assign one for that student to do. My third choice of target was this grill behind South Campus Commons 5. I chose it because of its very close proximity and basic shape that would be easy to pick up regardless of how high or low the resolution of my sensor turned out to be. My second choice of target was this fountain outside of the mathematics and engineering buildings. This fountain would still be a large target that would be easy to pick up regardless of sensor resolution. However, its unique shape and position on campus would provide a little bit more of a challenge to scan. My first choice of target, and the one I ultimately ended up scanning, is this statue of Mary and Jesus outside of the Catholic Student Center by South Campus. It was ideally located for me, and although I didn't realize it at the time, its matte white finish would provide an excellent return for my LiDAR sensor. There were some complications in terms of blockage of the back of the target due to the stone wall that you can see here, and I knew going in that it would be hard to capture the full level of detail that the statue possessed. There were some other perks, however. This stone base turned out to be the ideal reference geometry for assembling my 3 separate meshes into one. My main reason for choosing this as a target, however, was due to the very fine level of detail on the statue. I wanted to see exactly how much of this I could capture in the final point cloud. The LiDAR scanner I constructed as part of this project is made of several basic components. First, the tripod, which supports all the other equipment. Second, an external battery pack meant for charging phones that supplies 5-volt power to my Pi and my line laser. Third, the Raspberry Pi that's mounted on the 3D printed structure supplied by Dr. Mitchell. This is actually a slightly modified version of the STL file in order to make it print faster on my friend's 3D printer. This Pi supplies power to the line laser through a custom connection that I made with just DuPont connectors. And it is also connected in turn to the PiCam V2, also mounted to the 3D printed assembly. This assembly keeps it pointed in the same axis as the line laser mounted to the bottom of the same 3D printed part. From a remote sensing standpoint, this would be classified as an active LiDAR sensor due to the fact that it is emitting light and using that light in order to range to a target. However, it differs from what people conventionally think of as a LiDAR in that it is using geometry-based computer vision principles in order to determine the range to target, as opposed to the time of flight normally used in more powerful airplane and space-based LiDAR systems in order to range. We started off the project by constructing a simpler point laser-based version of our final LiDAR. While constructing my unit, I paid special attention to make sure that the laser and the camera center axis were exactly parallel and exactly 12 inches apart. I did this by measuring the distance between the center of the camera, which you can see here aligned with that tissue box, and the laser dot at a distance of about 20 feet, which is twice what we would use it at in the testing phase. This allowed me to very accurately align the laser and the camera. This device was then calibrated by ranging off of a white paper-covered box at known ranges of 0.5 feet to 10 feet. My precise alignment procedure paid off. The calibration curve was very well matched from the get-go. I only had to slightly tweak the values in order to match it up almost exactly. This gave me confidence that going into the next stage of the project, I could continue to maintain a high level of quality. Once the new line laser-based LiDAR was built, we replicated this calibration procedure. This is an image at 2 feet from my matte white apartment wall. As you can see, the line is almost perfectly vertical. This is very important as any skew of the line will affect the range measurements that the unit takes. This is due to the fact that it relies on the distance of each point on that line left of the image center in order to calculate the range to each part of that scan of the target. You can see here as we switch to a 3-foot range that the line became closer to the center of the image. Same for 4 feet, and as we do 5 and 6 feet, you'll see that it gets closer, but the amount that it moves continues to decrease. This indicates the presence of a sweet spot in terms of ranging ability, wherein inside that distance, the lidar will be able to range fairly accurately, and outside of it, accuracy will drop. This is due to the fact that at increased ranges, the difference between 1 pixel left and 1 pixel right becomes a much larger distance in reality. This is due to the geometric configuration of the sensor, as well as the resolution limits of the camera. My plan to image the target was fairly simple. I would take 3 different angle scans of the target to ensure that every single point on it was covered at least once with a laser scan. When I arrived on scene, however, there were some complications. Large amounts of vehicle traffic and the streetlights around provided some light interference. However, the main source of interference was not actually the vehicle traffic, but several lights mounted around the statue designed to illuminate it at night. You can see one of them pictured here. I solved this issue by covering them with a piece of cardboard. As you can see here, when I lift the piece of cardboard up, it illuminates the target to a degree that would wash out the laser light. My data collection process was fairly simple. My laptop was connected to my Raspberry Pi via Ethernet. I had had some issues with Wi-Fi, and so I decided to go with a simple wired solution. I used VNC in order to access the Raspberry Pi and execute the appropriate scripts. While scanning, I adjusted the angle at the minimum possible increment given the resolution of my phone's accelerometer output, in this case 1 degree. This gave me a large amount of images in order to generate a point cloud from. My 3 scans are shown here. This is the front scan, the right scan, and the left scan. As you can see, once I covered up the lights, the incredible darkness and the very high reflectivity of the target made for excellent image capture. This allowed me to generate a very high-quality final point cloud. Once I had gathered all of my image data, I used the provided Python scripts, specifically data generation, in order to turn them into a point cloud. In order to properly use this script, I adjusted both the selected folder and the color picker settings in order to get good results out of each image. The resulting point clouds for each of the 3 views that I scanned from were then uploaded into a program called Cloud Compare, which I then used to stitch each of the clouds together after trimming and filtering them. The main element that I trimmed away from each cloud was the reflections off of the stone wall behind the statue. This needed to be removed in order to get a better view of the actual statue itself. In order to do this, I used Cloud Compare's built-in cut tool, which separated the mesh into 2 different meshes, one of which I could then delete in order to leave only what I wanted. From then, I would repeat this process for each of the 3 meshes, and then using the key points on the statue, as well as the translation rotation tool in Cloud Compare, rotate each and translate each until they all lined up. From there, I used the merge tool to combine all 3 into one. I then took that mesh and using the cleaning statistical outlier removal tool, cleaned down the point cloud so that it would work better with MeshLab. The point cloud on the right, pictured here, is the original point cloud. The one on the left is the cleaned version. You can see that the points in the cleaned version align more closely, making it easier when we import it into MeshLab. In order to create a mesh of the point cloud, I used MeshLab in order to drape a virtual mesh over the existing point cloud. In order to do this, first I needed to define the normals for the point cloud. I found that the most effective method of doing this for my particular one was to use the viewpoint to define how the normals were positioned. This let me get most of them facing outward as opposed to other methods which position them entirely randomly. I then trimmed out the mesh and disabled the normals view. As you can see here, the final mesh compares very well to the original figure. Large details such as the heads, arms, bodies, even some of the folds in the clothes are captured. However, small details such as the rosary and more intricate clothing folds are not captured very well. I believe this is more of a function of the limitations of the sensor itself due to its budget-friendly manner of construction than anything else. I'm very pleased with how the final mesh turned out. I think it's very good considering the level of difficulty that this target presents. I was also happy to be able to image a target that was somewhat personally relevant, as I am an active member of the Catholic Student Center. I'd like to thank Dr. Mitchell, as well as my fellow students, for giving great aid and advice throughout the semester. I enjoyed the class very much, and I know that I will be able to apply the skills that I learned here in my future work.